Welcome back, guys. So today we are going to talk about some very important time functions which you will usually encounter in engineering, science and mathematics. Okay, so what are those functions, what are their mathematical equations, and where these can be used is basically the topic of this video. Okay, so the first and the foremost function here is the unit step function. Okay, so what is basically the unit step function? If you can see that in previous lecture we have used this in our DC circuit analysis as a DC source. Okay, so how these can be written, this is basically like here. Okay, so this is basically the unit step function, and as we are talking about the time function, so the x-axis here is the time, so therefore this is also represented as u of t. Okay, so that is the symbol of unit step function. Similarly here, this is the amplitude here remains constant and this is u of t. So if the amplitude increase or decreases, so that constant can be written as k. Okay, similarly there are many other versions of it, as it can also be written like here as well. Okay, where this can be a, and this is the delayed version, so that is ut minus a. Okay, with this amplitude as 1. Okay, similarly it can also be like here as well. Okay, it can also start from here, and if it is also a, so this function will be ut plus a, because this is the advanced version of my original signal which is mentioned here. Okay, so that is about the unit step function. Similarly, apart from these, we have also another function, that is the square wave function. Okay, so what are basically the square wave functions? These can be here, this is the square wave. Okay, so that is like we can see in the digital signals, this is one of the form in which it will remain at the upper side of this 0 axis. Okay, so this will be here, and that is basically the square wave. Similarly, another type you can also see here can be like, okay, so these are another type of waves where we can see that here some part of it is above the 0 axis while the other part is below it. Okay, so what is basically this? If this is my on part, okay, and that is the off part, and similarly the total time period it has is t. So what is it? There is a very important thing here, and that is called the duty cycle. Okay, so the duty cycle concept here is that is the on time with respect to the total period where we have on plus off time. Okay, so that is the duty cycle of my square wave. Similarly, the third type of wave which we usually can see here is the sinusoids. So what are basically the sinusoids? So the first sinusoid is the sine wave. This is the sine wave, okay, with t, and the second one here is, this is my x, the second one here is this cos wave. You can see the difference here, because at 0 instance here the value of my sine wave, if this is sine of omega t and this is cos of omega t, where this is t and this is t as well. Okay, and the amplitude they have are a. Okay, so you can see that it starts from 0, while at 0 instant it has the maximum value. So there is the 90-degree phase shift between sine wave and cosine wave. Similarly, we can see that here we have in sinusoidals we have basically three parameters. The first one here is this a, which is called the amplitude. Okay, the second one here is omega, which is the frequency, because omega is equal to 2 pi f, where f is in hertz while this omega is in radians per second. Okay, and the third one, which I did not mention here but it also available here, that is the theta, and that is the phase angle. Okay, so these are the three parameters which usually defined for the sine waves and the cosine waves. So this is the third waveform. The fourth one here, which is usually used, is the linear waveform, linear function or linear waveform. So as the relation between the x-axis and y-axis is linear, so that's why this will be like here. So that is the linear waveform where this f of t is equal to t. That is the mathematical function for this linear waveform, and it also can represent it for the negative time as well. Okay, so that is for minus t. Similarly, another very important waveform here is, that is the fifth one, and that is the unit impulse. So what is basically the unit impulse? So if you have this time axis here, so it lies here at this instant, such that the length it has is basically L and the width is W, so that its length approaches infinity while the width of it approaches 1 over infinity. Okay, so that is the unit impulse waveform, which is usually represented by this delta t. Okay, so that is for the unit impulse waveform. Similarly, also we have some other waveforms here as well, and one of them is the exponential waveforms. Okay, so exponential waveforms are usually of two types. One is the rising exponential, and we can represent them like this, where the function it has is exponential of at, while the second one here, if I can represent here, is that initially it has the highest value, but with the passage of time it decays. So therefore this is called that is the decaying exponential. Okay, so we have these two exponential waveforms. Okay, so that's it for the exponential. Similarly, two more waveforms. The seventh one here is the triangular waveform. Okay, so what is basically the triangular waveform? If that is the axis here, so the triangular waveform we will have like this one. Okay, so you can see the triangle which you can have here, so that is the triangular waveform which we can see here as well. Similarly, the last one here is also a very important waveform, and that is called the Sawtooth waveform. That is another function, and you can see that the Sawtooth waveform rises linearly, while at one instant it has a sudden jump. Similarly, then again it has a sudden jump, and here as well, and so on. Okay, so this is the Sawtooth waveform. And similarly, it can be like this one, where all the curves here are positive in the above the zero level, while another Sawtooth waveform can also be like okay, these can also be like here as well. Okay, so that is for t, that is for f of t. So that's it for these type of waveforms which we have seen, and you will seldom see their use in many applications. So therefore I have basically had a very important lecture for to introduce you with all the concepts related to these functions. Okay, so that's it for today, and I will see you with a very comprehensive lecture in which I will describe the S domain equivalent of these waveforms, which will be used to test our different circuits which will be in S domain. Okay, so that's it for today, and I'll see you in our upcoming lecture with some more interesting stuff. Till then, take care of yourself, and I will see you soon.